will not. I won't replicate anymore the things that you already see in Uble. What I'd like to do is more give examples of actual circuits. So this is the example that I provided last time. Okay. So this is a fixed bias. No, this is a fixed bias circuit. Okay, you have an input voltage that is fed into the base through a coupling capacitor that's C1. Okay. And then the output is taken from the collector. So this is actually a common emitter amplifier. Output is taken at the collector. Itong RL at saka CL, you might think of this as representing the input resistance and the input capacitance of the next stage. So there might be a second amplifier here, and this would be the input resistance and the input capacitance. Now, why do you need this? You need this because there's a DC component that exists at the output here, and you have to get rid of that DC component. So the function of C2 is the same as the function of C1. That is to get rid of any DC component that is present in your signal. At the same time, this one will isolate your input with respect to the DC biases. Because this acts as an open circuit for DC, whatever bias currents you have here will not go back toward the input signal. Same thing with C2. In this particular case, we assume that C1 and C2 are large, so that the effect of C1 and C2 is at the input signal frequencies, they act like short circuits. And then I gave you all of these circuit quantities. So the example is supposed to be determine the frequency response of this circuit. Okay, we'll do this in two parts. First part, we will neglect the effect of Cs of mu. Cs of mu is the capacitance from your collector to your base. You also call this the Miller capacitance. So first, we will neglect the effect of Cs of mu. Okay. To be able to get the small signal equivalent of this transistor, you have to know its bias conditions, because your small signal parameters depend on the Q point. For example, GM is equal to what? ICQ over V sub t. You need to know ICQ. No? R pi is equal to beta over GM. No? So you need to know GM to be able to get R pi. Anyway, you need to know the Q point. No? And it's easy to get the Q point because this is a fixed bias circuit. For purpose of determining Q point, we can assume that this being silicon, VBE is equal to 0.7. Now, if you're given the reverse saturation current of the transistor, then you would have to compute VBE using the exponential model of the transistor. But if you're not given that, no, then you can assume this being silicon, VBE is just equal to 0.7. And then you can compute for, sorry. Okay, you can compute for IBQ, no? So this is IBQ. Okay, this is that's just equal to VCC minus VBE all over RB. Okay. And if you compute for IBQ, sorry, after computing for IBQ, you can compute for ICQ. Which is equal to beta IBQ. And you're just going to get, I'll just give you the result. This is going to be 540.54 microamperes. And so now I can get the small signal parameters of my transistor. Okay. Ito yung GM, ICQ over V sub t. It is given here that this is at room temperature. Circuit is operating at room temperature. ICQ over V sub t, I'm going to get 20.79 millisiemens. I can get R pi, that's beta over GM, 4.81 kilo ohms. And then I can compute for C sub pi because I know my transition frequency, 600 megahertz, and I'm also given C sub mu. You recall that last time we computed for a way of determining your transition frequency. No? That's omega sub t is equal to G sub m over C sub pi plus C sub mu. No? So from there, I can compute for C sub mu. And so now I can draw my small signal model. And this is what my small signal model comes out to be. So recall that I did not include in my small signal model Cis of mu, which is between my collector and my base. No? Because we're neglecting the effect of Cis of mu for the meantime. So hindi ko palinagay dito yung Cis of mu. Okay, so let's say the problem is, what is the frequency response, no, of your gain? Because you're supposed to construct the body plots of the voltage gain of the amplifier. So I have to get an expression for V sub O over V sub S. That's my gain. No? AV is equal to V sub O over V sub S. So how do I do that? The way I do that, first I can do a KCL here at C. Okay, now in doing that KCL, I simplified my circuit. No, how did I simplify my circuit? Itong R sub B, right? That's this. So remember that because this 1.5 at small signal is grounded, itong R sub B ends up being parallel with R pi. And if you get the parallel combination of these two, this is 4.66K. On the other hand, R sub C ends up being parallel with R sub L and R sub O. But R sub O is equal to infinity because my my early voltage is equal to infinity, therefore R sub O is equal to infinity. Remember that this is equivalent to a short circuit. So I just have R sub C in parallel with R sub L, that's both 1K. So the parallel combination now is 500 ohms. So this is now my simplified small signal model where I already put R sub B in parallel R pi here, that's 4.66K. And then my RL in parallel with RC, both 1K, so this becomes 500 ohms. Okay, so doing a KCL here at C, KCL ako rito. Okay, what are my current components? No? First of all, I sub O is equal to 0 because this is open circuited. Remember, we're getting the ratio of V sub O over V sub S. This is at no load, but at no load here has to be an open circuit because if we short this, mawawala yung V sub O natin. So it has to be an open circuit. So what are my current components? The current going down my 1 picofarad is V sub O times 1 picofarad times S. It's actually V sub O divided by 1 over SC. No? But V sub O divided by 1 over SC is V sub O times SC. So it's just V sub O times SC. C is 1 picofarad, S is my S variable. No? Okay. So that's the current going down here. No? The current going down here is V sub O over 500. And then the current going down here is 20.79 M multiplied by V sub B, where V sub B is the small signal voltage from my base to my emitter. So ito yun, V sub B. So this is my first equation. So simplifying that just comes out this. Because 1 over 500 is 2 times 10 to the minus 3 or 2 milli. So this is your first equation. Okay. Now I want an expression of V sub O over V sub S. What I have here is V sub O and V sub B. So what I need to do next is express this V sub B in terms of V sub S. And that's quite easy to do. You can just use voltage divider here. No? This is one impedance, this is another impedance. You can just use voltage divider. Of course, you could have used any other method. You could have used nodal analysis, or you could have used a KCL. So using voltage divider, the parallel combination of 4.66K multiplied by 4.71 picofarad. Okay, when you have a resistor in parallel with a capacitor, when you have a resistor, in parallel with a capacitor, so this is R, this is 1 over SC. What is Z equivalent? Z equivalent is just going to be R over 1 plus RCS. Because if you do product over the sum, no, what's the product? That's R over SC. The sum is R plus 1 over SC. If you multiply the numerator and denominator by SC, lalabas you just have R over 1 plus RCS. No? Okay, so what's the parallel combination of this? The parallel combination of this is 4.66K divided by 1 plus 4.66K times 4.71P C. So ito yun. No? This is the parallel combination of these two. So voltage divider. No? So this is V sub B is equal to V sub S multiplied by itong impedance na to divided by your total impedance. Your total impedance is 1K plus the parallel combination of these two. So that's my denominator. Okay, now what I'd like to do before substituting this, because ito, ang intention ko, ito, I will substitute this into this. Right? I want to substitute 2 into 1 here so that I can get an expression for V sub O over V sub S, which is what I want to get. No, that's my gain. But what I would suggest you do is you first simplify this. Okay, how do you simplify this? Well, let's do a little bit of simplification. You have V sub B is equal to V sub S. Okay, 4.66K all over 1 plus 4.66K 4.71P S. Okay. And then yung baba, let me already cross multiply. So I have 1K. I multiply that by 1 plus 4.66K 4.71P S. Yan, no? So ito kinross multiply ko na ron. Okay. Plus this one, 4.66K. Now all over 1 plus 4.66K 4.71P S. And notice now I can cancel this too. Okay. And then I simplify this. I just simplify this. So I multiply my 1K into this quantity. I multiply my 1K into this quantity. And then I can add 1K here to 4.66K. I'm going to get 5.66K. So I'm just going to end up with two terms in my denominator. If I do that, ito yung lalabas. So ito na yung numerator ko, 4.66K, that's this. Remember, I have 1K plus 4.66K, that's 5.66K. And then if I multiply this 4.66K multiplied by 4.71p, this is what I'm going to get, 21.95 micro multiplied by S. And then I can further simplify this so that it's close to my standard form. Remember my standard form, I want it in the form of 1 plus, eventually, 1 plus j omega over omegas of p. So linalagay ko na yun close to the standard form here, no? I factor out 5.66K, and then this is now 1 plus S over, and then yung denominator ko is just this divided by 5.66K, and then you get the reciprocal. And that comes out 257.88 M, no? Mega. So that's my attempt at simplifying itong equation number 2. Okay, why I wanted to simplify this too is this, Notice that this is an expression for your base to emitter voltage as a function of your source. Knowing your source, you can get your base to emitter voltage. And you can see that the relationship between your base to emitter voltage and your source voltage, the relationship, there is a pole that is introduced. There's a pole that is introduced in my relationship between my base to emitter voltage and my input voltage. Okay, notice that this is a pole. That pole is due to the existence of your CPi. Dahil nagkaroon tayo ng base capacitance, which is CPi. Remember CPi that consists of two components, but never mind, no? Basta't alam mo that there's a base capacitance. Because you had a base capacitance, you combine that with RB, RPi, and RS. Those are all of the resistors that are connected to that particular capacitance one way or another. No? RPi and RB are parallel to the capacitance. RS is in series with the capacitance. No? But this resistor in combination with this capacitor will result in a certain time constant. No? And your zero frequency is 1 over that particular time constant. Yung your pole frequency is 1 over that time constant. And if you compute for that, you're going to get ito, 257.88 M, meaning 257.88 mega radians per second. Remember that this is in radians per second. If you want to convert this to hertz, what you have to do, you have to divide by 2 pi. No? Because 2 pi f is equal to omega. So this is in radians per second. Okay? So that's what I wanted to point out here. No? Because of the capacitance here, no, because there's a CPi here in effect. Okay, remember that this is considered a short circuit because there's a CPi here. Nagkaroon tayo ng pole that is introduced at the input. And the pole frequency is given by this, no? Okay, which you can work out. That's CPi. That's CPi in parallel with RPi and RB in series with RS. Okay, so now I can substitute this into 1. No? So this is my equation number 1. Itong values of B sub D, pwede ko ngayon i-substitute dito sa loob ng 1. What am I going to get? Okay, I'm going to get this. Okay. I'm not going to go through too much detail anymore of the computation, no? Because that's just simple math. That's just simple multiplication and distribution. Okay? But notice now, I can manipulate this equation so that I can get an expression for V sub O over V sub S. So ito ilalagay ko lang dito sa kabila, and then I can just now get the ratio of V sub O over V sub S, which is my A sub V. So you can do that on your own as an exercise. Okay. My numerator is 20.79 M multiplied by 4.66 K. Okay. My denominator will be this denominator. So notice this is my input pole. And then this will go into the denominator also, no? Itong 1 pico over 1 pico, yeah, plus 1 over 500 will also go into the denominator. Itong term na to. Okay. And this actually, once it goes into the denominator, also becomes a pole. So notice now I have two poles. This is one pole, which I already associated with my input. And this pole, okay, this pole will now be associated with my output. That pole I got from applying KCL at my collector, which is at the output. Now, ang ginawa ko, itong 1 over 500, I factored that out because I wanted it to be in standard form. The standard form is dapat 1 plus S over something. 1 plus S over something. Right? So I factored out here 1 over 500. Dito naka-factor out na yung 5.66K kasi naka-standard form na to. And then the next step is ito, ilalagay ko sa denominator, no? Itong 500p. So the reciprocal of 500p is 2g. 1 over 500 times 10 to the minus 12 ends up being 2 times 10 to the 9. So ito ngayon yung, and then I combine, no? 20.79 M multiplied by 4.66K divided by 1 over 500 divided by 5.66. So now my DC term ends up being 8.56, a single DC term. And then now this is now in the form that I want. Okay. So how do we get the frequency response? Ano yung susunod? Once you have it in this form, you just replace S with J omega. Yun, no? You just replace S with J omega. Okay. So it's a two-pole system. This was introduced at my input. So I have an input pole at frequency 257.88 megaradians per second. This pole, okay, this pole was introduced by my output capacitance. That's introduced by this capacitance, C of L, that caused my output pole. So the value is 2G. Okay. Note, no? What is the resistance that is seen by my 1 picofarad? That is 500 ohms, no? 500 ohms. If I get if I get RC, okay, and then I get the reciprocal of that, ang lalabas that's equal to 2G. Okay, that will be equal to 2G. So this is the output pole. Okay. So now my gain consists of a DC component and then an output pole and an input pole. And so now using the techniques you learned earlier, you can now determine the frequency response. Okay, so what will your frequency response look like? Well, your first term will be 20 times log of 8.56. Remember, when you're getting the DC component, you only get the magnitude, no? You take out the negative sign. The negative sign is accounted for later on. You have to add 180 degrees to your phase. So you start with 20 log 8.56. So if you do that, that's about 18.65 dB. Okay? 18.65 dB. Okay. And then this is constant until you hit omega P1. Omega P1. Ano yung omega P1? That's 257.88 megaradians per second. Okay, 10 to the 8 is 100 megaradians per second. That's 100, 10 to the 8, no? So 100 times, or yeah, what's that? 10 to the 8, 10 with 8 zeros, no? So 1 megaradian per second is 10 to the 6. 100 megaradians per second is 10 to the 8. So 10 to the 8 is 100 megaradians per second. We're at 257 megaradians. Ang midpoint between 10 to the 8 and 10 to the 9 is about 360 megaradians. So it will be a little left of the midpoint. Little left of the midpoint, what will happen here? By how much will this go down? By 20 dB per decade, no? Because of this pole. So bababa siya by 20 dB per decade. No? So from here to here, so this is 1 decade. Okay, so this is to the right of 10 to the 8. This is to the right of 10 to the 9, the same distance. Okay, you're going to go down from 18.65 to minus 1.35. No, you just subtract 20 from this. 18.65 minus 20, you're going to go down to minus 1.35. Ano ibig sabihin ng negative gain? Ibig sabihin, less than 1 na. Because this is your 0 dB, this is where your gain is equal to 1. When you go below 0 dB, that means your gain is already less than 1. Your output is already smaller than your input. Okay? So, yun, no? So you continue going down. No? So lalampas ka dito sa point na to. Right? Lalampas ka rito, you're still going down 20 dB per decade. And then as soon as you get to 2 gigaradians per second, giga is 10 to the 9. 2 is 10 to the 9. Tama ba? Mali pa pala yung drawing ko rito, no? Yeah, well, anyway, no? I didn't draw this exact, no? But this will continue going down. And then at the point where you are, ito pala yung 10 to the 9, sorry. Okay, that's right. This is 10 to the 9, so 2 gigaradians per second will be right of 10 to the 9, midpoint between 10 to the 9 and 10 to the 10, no? Left of midpoint. As soon as you get to 2 gigaradians per second, what happens? Your deceleration will add by another 20 dB per decade. So magiging 40 dB per decade na. Okay? So here 20 dB per decade. Pagdating dito sa 2 gigaradians, magiging minus 40 dB per decade. So that's how your magnitude of your frequency response will look like. Any questions? Any questions? Now the phase response well, this is a little bit harder, yung phase response. Ano? So you start with 180 degrees, okay? Because your DC component is negative, no, your DC gain is negative. So you have to start at 180 degrees. And then your first zero, this is the input pole. So this is omega P1, 277 megaradians per second. You're going to go down by 45 degrees per decade, or 90 degrees for 2 decades, from 0.1 of omega P1 to 10 of omega P1. So you're going to start at, let's say, 277 megaradians per second. You're going to start at 27.7. 27.7 megaradians per second. Okay, at 277 megaradians per second, you'll be at negative 45 degrees. And then at 277.0 megaradians per second, you'll be at minus 90 degrees. So you have this. That's for the input pole. And then for the output pole, this is at 2 giga. Okay, so should be somewhere here, no? Anyway, this is not drawn to scale, no? So you can just do this on your own, being more accurate. So you're going to start at 2 giga. So you start at 0.2 giga, 2 giga, and then 20 giga. And then this will go down by 90 degrees between 0.2 giga and 20 giga. So this is your second graph. So you have to add 180 plus this plus this. And if you do that, okay, you're 180 until you reach 0.1 of omega P1. Then you're going to go down to by minus 45 degrees per decade, no? Until you reach until you reach omega P1. Until you reach omega P1, then you're going to go down by 90 degrees per second, per decade rather, until you reach omega P2. No, sorry, until you reach, well, wherever, no, this intersects with this. Then after that, since ito zero na, ang matitira na lang dito is minus 45 degrees per decade. I'll try to clean up this, so that when I publish it, it's a little bit cleaner. But it's just a matter of adding the 3 graphs. No? Suggestion ko, when you create the graphs, try to be as neat and as accurate as possible, because if you're not, it's easy to make a mistake. Any questions? So that's the example that I wanted to present. No? So this is just for the gain. This is just for the gain. Notice that you can have a body plot. Pwede ka magkaroon ng body plot, not for the gain, but for the transconductance. What I computed for here was V of O over V of S. But I could have computed for G's of M. G's of M would be what? Ano yung G's of M? Kalimutan na ninyo. V of O over I of I, di ba? No? G's of M is V of O over I of I. No? And if you compute for G's of M, you can also get a complex formula, a complex function, which has poles and zeros. And so there's also a body plot, for example, for G's of M. There's also a body plot for R's of I. There's also a body plot for R's of O. So the example I gave here is creating the body plot for A's of V. But all of those parameters, G's of M, R's of I, R's of O, can have corresponding body plots. In other words, you might want to know how the input resistance will vary with respect to frequency. You can take a look at the body plot for R's of I. Now, the other thing that I wanted to mention is, ano ba talaga yung effect nitong capacitors na to. This will have effect at very low frequency. Okay. Now take a look at this. No? So this is supposed to be ace of j omega. No, this is supposed to be my gain, and my gain has a certain value at DC. No? Well, this is not DC. No, this is a frequency of 1, because you cannot show a frequency of 0. You cannot show a frequency of 0 pag log scale. No, because you cannot represent. I mean, you can go closer and closer and closer to 0, but you will never really get to 0 at log scale. No, but yeah. So let's say we're approximating this to be DC 10 to the 0, which is a frequency of 1 radians per second. Notice that I have a certain value of gain. But at DC, what is a capacitor equivalent to? It's an open circuit. If it is an open circuit, ibig sabihin, none of the input will enter the amplifier. Kasi may open circuit ka ron, no? At DC. If none of the input can enter the amplifier, what is my gain? My gain is 0. So you can see that this is not exactly accurate at low frequency. And the reason for that is, yun nga, no? We disregarded this, and maybe even this, ano? We just assume that they're short circuits at all frequencies of the input. Pero sa totohanan, at DC, that is not a short circuit, that is an open circuit. So the more accurate picture of your gain, no? Although it really only happens at very low frequencies, if you wanted to get a more accurate picture, your gain would be actually 0, no? 0 at DC, and then it will increase that way. And the point at which it increases depends on the value of my coupling capacitor. And this gain, no, we actually refer to this, may term tayo rito, we refer to this as the mid-band gain. No? Because most of the time we will be operating here. No? In other words, we want our amplifier, for example, to have a constant gain between a certain frequency and a certain frequency. So we design our amplifier that way. We design the location of our poles and zeros so that we achieve a certain what we call mid-band gain. No, usually we don't operate it here in this region because babagsak na yung gain natin. So this is a more accurate picture. If I had included this in my analysis, in other words, hindi ko inassume ito na short circuit, no? If I had included SC1 in my small signal model, I can actually determine exactly when this happens. No? Exactly when this happens. Sorry. Okay. But usually we don't do that anymore, no? Basta't alam natin that at low frequencies, walang dadaan na signal. But if you want to know the exact, you can actually include C1 or C2 in your analysis. Okay. Let's make things a little bit more interesting. What will happen now if I consider C sub mu? Ang mangyayari lang, if you consider C sub mu, ito will be exactly the same, except that I would have a capacitor here. Okay. Medyo tinatamad ako. I don't want to redraw this. Let me just copy this slide. Okay, so yeah. So if I want to consider C sub mu, dito ko lang siya ilalagay. Right? So if I do now a frequency analysis of this, I will see what the effect of C sub mu is. Okay, now this is going to be obviously more, how do you say it, no? It's going to involve a little bit more mathematical manipulation. So the same principle, we'll apply the same principle. First, we'll do a KCL here. So let's do that. KCL at C. Okay, what are my components? My current through my 1 picofarad is going to be like this, no? It's going to be V sub O 1PS. No? V sub O over 1 SC, no? So it's just V sub O times SC, so V sub O times 1PS. My current going down here is V sub O over 500. But V sub O over 500 is V sub O times 2M, because 1 over 500 is 2M. So this is plus V sub O multiplied by 2M. And then I have my current here, okay, plus 20.79 M V sub B. Kanina, doon tayo tumigil. Pero ngayon, meron din akong current rito. Okay, what is the current here? Can you help me out? Can somebody help me out? Ano yan? V sub B. No. Yung current here going to the left. Okay. So that's going to be V sub O minus V sub B multiplied by, ano yung value ng C sub mu? Ay, kalimutan ko. No? So 0.8, no? 0.8 picofarads, sorry. 0.8 picofarads, no? So V sub O minus V sub B multiplied by 0.8 PS. So these are 4 current components, no? One going down here, V sub O 1 PS. The one going down here, V sub O 2M. The one going down here, 20.79 M VB. And then the one going left here, which is V sub O minus V sub B 0.8 PS, should equal to I sub O. But since this is an open circuit, that should equal 0. Let me try to simplify this a little bit. Okay, I can combine this. So this is V sub O 1 PS, and this is V sub O 0.8 PS. So I can combine the two. So that's V sub O 1.8 PS. And then here I have V sub O 2M. And then here I have, yun lang pala, no? plus 2m, no? Plus 2m. Okay. Is equal to, so ito tapos na, ito tapos na, ito tapos na. Okay. V sub B 0.8 PS minus 20.79 M. Okay, so this is my first equation. It defines a relationship between my output voltage and my base to emitter voltage. Okay. Now, how do I get my gain? No, I have to express now V sub B in terms of V sub S, but in this case, it will be in terms of V sub S and V sub O, because I have this. No, and then I'm going to have to do some manipulation. Okay, so I'm going to do a KCL at my base. Okay, so what is my, okay, I'm going to do KCL here, no? Dito, this particular node. So what is this current? What is this current? V sub B minus V sub S over 1K. Okay. Don't just copy, no? Anyway, I'll provide you this. No? Try to think about it. No? You have to try to follow. V sub B minus V sub S over 1K. What is the current going down here? That's V sub B over 4.66K. Okay. And then you have a current going down here. Right? So that's V sub B multiplied by 4.71 PS. Okay. And then finally, your current going to the right here. Okay. So that's V sub B minus V sub O multiplied by 0.8 PS. And that should be equal to 0. Okay? 4 terms. This current, 1, 2, 3, 4 should equal 0. So just KCL, just nodal analysis. Okay? Let me again try to simplify this. So let me separate the different terms. No? First, I have V sub B 1 over 1K plus 1 over 4.66K plus 4.71, PS, okay, plus 0.8 PS. So those are all the V sub B terms. And then I have minus V sub S over 1K. And then I have minus V sub O times 0.8 PS. This is equal to 0. Finally, okay, what is V sub B? I just transfer this both to the other side of the equation, then divide it by this after simplifying this. So let me do that. I'm going to come out with this, no? V sub B is equal to ito, no? V sub S of ito, this is V sub S over 1K is V sub S times 1M because 1 over 1K is 1M, no? So this is V sub S times 1M minus plus V sub O kasi ililipat ko sa kabila to, no? Magiging positive. V sub O times 0.8 PS all over, and then I just simplify this. 1 over 1K plus 1 over 4.66K is 1.215 M. No, this is 1.215 M. No? I hope my calculations are correct. I only did this before coming here. No? And then ito, 4.71P plus 0.8P is 5.51P. No? Sorry. Mali. 4.71. Okay. Yeah, tama, no? 4.71 plus 0.8, yeah, is 5.51P. Mali yung notes ko. Yeah, 5.51P. PS. So this is now my second equation. So what I do, I substitute my second equation into my first equation. Itong expression ko for V sub B, my expression for V sub B, I substitute into this. Okay. You can already see that this is going to be a very involving process. Ano? Okay, so let me just, sige, let me write that out. So V sub O multiplied by 1.8 PS plus 2M is equal to this is V sub O no sorry V sub S 1M plus V sub O 0.8 PS all over 1.215 M plus 5.51 PS multiplied by this. 0.8 PS minus 20.79 M. Okay. Okay. Now notice that I have a V sub O term here. No? Meron akong V sub O term here that I have now to put back into the left side. Right? So okay, so I'll work on that, no? So that's V sub O. V sub O 1.8 PS plus 2M. Okay. That's going to be minus 0.8 PS 0.8 PS minus 20.79 M all over 1.215 M plus 5.51 PS. So that's now my left side. Okay. Is equal to V sub S 1M 0.8 PS minus 20.79 M all over 1.215 M plus 5.51 PS. Okay. Kailangan pag ginagawa niyo yung mga problem na ganito, maingat kayo, no? Because you just make one small mistake in one digit and everything goes to waste, no? So anyway, you can already see where we're headed, no? Now the next thing that I might want to do is I might want to get rid of the denominator here. So I multiply both sides of the equation by ito, no? By 1.215M plus 5.51S. So itong term na to will go up here. Okay, let me just try to go through the steps with you, and I encourage you to try this on your own, no? Itong term na to will multiply up here, and then ito will cancel, no? Sige, let's go as far as that, no? As far as that. So I'm going to get V sub O 1.8 PS plus 2M 1.215M plus 5.51 PS minus 0.8 PS 0.8 PS 20.79 M is equal to VS 1M 0.8 PS minus 20.79 M. Okay. And then now, I can multiply this out, and combine terms. No? If I multiply that out and combine terms, okay, I'm just going to tell you what is going to come out, no? Okay, the highest order here is S squared. No? Notice here I have S squared. Here I also have S squared. 1.8 PS multiplied by 5.51 PS. I'm going to get S squared. So my highest order there is S squared, no? So I'm going to get something like here, AS squared plus BS plus C. That's what I'm going to get here. Okay. And then here, I'm just going to get something like DS plus E. No? Something like that. Because here the highest order is just S, no? So I just multiply this into this. I'm going to get something like DS plus E. Okay. So if you take a look at V sub O over V sub S, no? V sub O over V sub S, what do I have? No? I'm going to get something like DS plus E over AS squared plus BS plus C. What is this? This is a 1-0 two-pole system, right? You have a 0 here. You have 2 poles here, because I can rewrite this in this form, no? This is going to be E multiplied by 1 plus S E over D, right? Okay, so this is already in standard form. No? And then here I will have 2 roots, right? If you factor this out, well, first you have to factor out the A, no? You have to factor out the A, then you're going to have something like S squared plus B over A S plus C over A. And then this will have 2 roots. No? So this will be of the form something like S plus, ano na ba tayo? A, B, C, D, E, F, and then S plus G. Something like that. No? A, B, C, D, E, F, G, these are quantities that you have to compute for. Right? And then if you put this in standard form, no? Ilalagay mo pa to sa standard form, is going to be F 1 plus S over F, and then G 1 plus S over G. So makikita mo na yung yung pole frequencies natin. You're going to see our pole frequencies. No? So at the end of the day, what are you going to have? You're going to have 1, 0, 1, 0, 2 poles, and then you can now see what your pole frequencies are going to be. Okay? So ano yung nangyari nung naglagay tayo ng Cs of mu? No? Nung naglagay tayo ng Cs of mu, all of a sudden nagkaroon tayo ng 0. That is the effect of Cs of mu. Cs of mu managed to create a 0 in my gain transfer function. Okay, if you, I'm sorry, no, I don't have because I noticed I made a mistake. Even me, no, I was doing this earlier and I noticed I had the wrong addition, so I don't have the final figures. But if you take a look at this frequency, because the value of Cs of mu is very small, this frequency ends up being very high. In other words, the effect of the 0 will be felt way to the right of your plot. Nandun sa kanan na ng plot. That's when you'll start to see the effect of the 0. And that's why sometimes we can disregard Cs of mu. Kasi masyado nang malayo sa kanan yung effect niya. What is the effect of a to the gain? No? The effect of 0 to the gain, it increases, di ba? Yung shape niya is pataas by 20, it adds 20 dB per decade. No? It's like the effect of a pole, which is to decrease by 20 dB per decade. Okay, so I'm just giving you in a gist what you should expect. No, now I encourage you tuloy nyo yung solution so that you get a feel for what this frequency is, and then you're also going to see that these particular frequencies, well, ma-affect yan ng Cs of mu. No? Itong F at saka G, that will be affected by Cs of mu. But you're going to see that it's not going to stray that far away from what we computed earlier. Meron pa ring variation pero hindi lalayo masyadong malayo dun sa kinompute natin kanina, no, when we did not consider the Cs of mu. Okay, I just wanted to discuss. So please, no, try to continue this, no, para may feel kayo for the process. Now there's one thing that I wanted to discuss, and that is the Miller effect. Yung Cs of mu, we call it a Miller capacitance. No. Okay, why do we call it a Miller capacitance? That's because of the Miller effect. The Miller effect is the following. If I have an amplifier and the gain of my amplifier is negative A, no. In other words, let's say I have an input signal here, and let's say this is V sub I. Okay. And let's say this is V sub O. Okay. So I have an amplifier whose gain is negative A. What will happen if I put a capacitor between my input and my output? So let me call this Cs of mu. And this is what we did earlier. Yung output natin nasa collector, yung input natin nasa base, naglagay tayo ng capacitor. Okay. You have a certain current here, no? Let's call this I sub X. Okay. Okay. If I sub X is approximately 0, let me compute for this. No? What is this current going to be? Sandali. Okay, if I of x is approximately 0, then itong I of I here will be approximately equal to this I of I. So kung ito is approximately 0, lahat ng current dito pupunta. Okay, it will go up there. Okay. Now I of I is equal to V of I minus V of O multiplied by S CU. Right? But V of O over V of I is equal to minus A. So note, no, this will work only when you have a negative gain. No? This particular relationship will work if you have a negative gain. And therefore, V of O is equal to negative A V of I. So ito, I substitute here. Okay. So I of I is just now V of I I of I is equal to V of I 1 plus A, 1 plus A, because negative V of O is negative A V of I, no? So 1 plus A S CU, okay, let me put CU S. Okay, what does this look like? No? Yung 1 plus A multiplied by CU, this looks like a capacitor across the input whose value is 1 plus A C mu. In other words, no, if I had redrawn the circuit this way, so this is, let's say, 1 plus A C mu I of I, V of I. How do I get I of I here? Assuming that I of X is equal to 0, no? Which is the same here. No? Hindi ba I of I is just V of I multiplied by 1 plus AS, 1 plus ACUS. Right? So I get the same thing, no? If I multiply this by 1 plus A, and then I connect it across my input, I will come up with the same expression for I of I. The two will act identically. Of course, that relies on itong current na to being approximately equal to 0. Okay, okay, so that's why this, even if this is very small, that's why that can have a significant effect in your circuit. No? Because even if this is very small, with respect to the input, it is multiplied by 1 plus A. So if A is large, biglang lumalaki yung effect ng capacitor na yon. And that is what you call the Miller effect. The Miller effect, no, is how a feedback capacitance ends up being multiplied by the gain at the input, no? Seen at the input as being multiplied by the gain, no? That's the effect of the amplifier. By the way, I can do the same thing at the output. I can do the same thing at the output. Okay. So I sub O, so if I think of I sub O, is equal to V sub O minus V sub I multiplied by S CU times S, ano? But V sub I is equal to V sub O, negative V sub O over A, no? Because yeah, V sub O over V sub I is minus A, so V sub I is negative V sub O over A, no? So this becomes what does this become now? V sub O 1 plus 1 over A C sub mu S, no? Okay? So ang effect is this. Para kang may capacitor dito na yung value is 1 plus 1 over A C sub mu. Now if A is large, then it's approximately equal to C sub mu. No? And usually A is large. Usually this is large, so usually this is negligible. Okay? So parang yung capacitor dito sa taas nakakabit lang sa output natin. So the Miller capacitance has a significant effect on the input, not as significant an effect on the output. Again, that relies on this being approximately equal to 0, no? That condition is usually the case sa input, but not usually the case sa output, no? So of course, this will introduce certain errors, no? But it can be used. It can be used to approximate the effect of the capacitor. Now, why did I introduce this, no? Because notice that yung previous example natin, ang hirap ng ginagawa natin, ano, basically. Imagine this is only one transistor. We considered the different capacitors, and we had to go through all of this. In fact, hindi nga natin ginawa, no? I just outlined the solution. We have to go through all of this manipulation to get our frequencies, no? I could have just used my previous, I could have used my previous analysis here, no? Okay. If I already know the gain of this, kung alam ko na yung gain nitong amplifier na to, okay, then when I add C sub mu, I will just put that in parallel with this. No? Yung 1 plus A C sub mu, I just put in parallel with this. Okay. And then yung 1 plus 1 over A C sub mu, I just now put in parallel with this. And my process now becomes simpler. So you can do that, no? Like I said, it's not going to be as accurate because it relies on, well, dito, okay, if I connect a capacitor here, talaga namang 0 yung current dito, no? Well, no. No, I can't say that. No? Forget what I just said. No? So again, no, It won't be as accurate because it relies on the input current being equal to zero. But at least it gives you an idea of what the effect of the capacitor is, and acceptable results. Acceptable naman yung mga results. Okay, that's all I wanted to discuss now. Okay, I don't have time to discuss a lot of the material. Nag-publish na madaming lectures dun sa module 6, ano? What I'll probably do, our last session that is on Thursday, I'll probably jump to the last part, ano, na just showing you a few examples of yung ibang configurations. Kasi common emitter lang to, what if it is a common source, no? Or a common gate. So we'll just go through some of that, no? Just to wrap up the course. So again, this is supplemental. Please study the official material for the course. Okay, so that's all for this afternoon. Any questions? Okay. I'm glad that you four are still sticking it out here. I hope it pays off on your part. No? Okay. Thank you.